Hello. Hope everybody is well. I hope you have a nice Easter also. I want to talk today about section 6.2. As I mentioned when we did the last slide, what happens in chapter 6 is that we take the ideas of confidence interval and hypothesis test and apply those ideas in a variety of different contexts. Basically what happens is that we give you a formula for the confidence interval and a formula for the hypothesis test, and we just iterate over different circumstances. All the different formulas are on the same page in the book. Oh, I got a little marker here, page 478. All the different formulas are on the same page in the book, so mark that page, and you might put a couple of other things on that page, little things to remember kind of thing. And every one of the formulas has a little twist. But if you understand the idea of confidence interval and you understand the idea of hypothesis test, it's just a matter of saying to yourself when you read the question, which context are we in? Is this a percentage context or is it a mean context? Kind of stuff. And once you have the right context, you run your finger down that page, find the right formula, and apply it. Now, a person needs to practice these kind of things. And like I said, every one of them has a little twist. But nonetheless, the idea of what a confidence interval is and the idea of what a hypothesis test is really the core of what a person needs. And the formulas, generally, been my experience, just simply don't give people trouble. Okay, so you can see, because it's on the screen, that section 6.1 was on percentages, section 6.2 is on means. So we're going to find a confidence interval where we know x bar and we want to figure out where does mu lie, and we're also going to do a hypothesis test where we might have an x bar and we're worried about is the true number, say less than 75. So the same ideas we've been doing from chapter 3 and chapter 4 applied in a new context. Now every context has some small twist, but nonetheless they typically work very smoothly, and this section's a perfect example. Okay, so first we need a formula that says if you are taking x bars and you're in search of mu, what's the center of the sampling distribution and what's the spreadedness of the sampling distribution? So of course, if you're taking x bars and you're in search of mu, the center of the distribution is you expect to be the true number. When you take the x bars, the center of the sampling distribution, you expect to be the true number mu, and the spreadedness, it turns out, is the standard deviation of the population over the square root of the sample size. So if, for example, the sample is of size 25, then you take the standard deviation of the population and divide by square root of 25 is 5. Okay, so that the samples are less spread out. It would be the original spreadedness of the whole population divided by 5, less spread out than the entire population. Okay, and there are contexts sometimes where you happen to know the standard deviation of the underlying population. I'll just name an example that everybody's familiar with. So everybody, maybe not everybody has taken, but everybody has heard of the SATs. And in the SATs, the center is 500, and the center of, say, the math SAT is supposed to be 500. Every year it varies a little bit from what it's supposed to be, but anyway, it's supposed to be 500. And the standard deviation, sigma, of the SATs, the one person at a time standard deviation of the SATs is supposed to be 100. So it is the case sometimes that you know the standard deviation of the underlying population. We'll deal in just a second with the more common case that you don't know the standard deviation of the underlying population. But at the moment, it's sometimes the case that you do. So I'm going to do an example of that, and I'm simply going to do a hypothesis test just to do one of the two instead of confidence interval, simply because hypothesis test often gives people more trouble than confidence interval. So let me bring up my example here. I have I think a person can read it. So I have a question. I went to another book just so that we'd have more examples than simply if I use the book that we have in class. So I scrounged a book from my office, and I'll read it to you since it's not perfectly clear on the screen. It says the technology site cnet.com publishes user reviews of computers, software, and other electronics. The mean user rating on a scale of 1 to 10 for the XPS 410 desktop computer was 7.2. So that was the nominal number, and then assume that the population standard deviation of user ratings is known to be 0.9. So they do these many times, and so they over a wide range of machines, and it always comes out to be something like 0.9. A random sample this year taken of 81 user ratings showed a mean of x bar equals 7.05. So the question is, has the mean rating fallen since the original number was published? Okay, so we have a nominal number of 7.2. Today, something like 10 years on, today the number is 7.05. And the question is the difference a sampling thing, or is the difference represent something for real? Okay, let me copy all this stuff down here. So I have here, let's see, a hypothesis test. And we're asked about means, not percentages. That was section 6.1, means. Okay, so we're arguing not about x bars, but instead about mu's. Never the sample numbers, always the population numbers. This is always an equal sign, always. And now, of course, you have to read the question sometimes 2 or 3 times to figure out what you're doing. But I think the nominal number here is supposed to be 7.2. You no longer have it on your screen, but it says whether the population mean user rating has fallen since 2007, and 7.2 was the 2007 number. Okay, if you don't write the same number in both places, it wouldn't be an argument. It'd be the kind of stupid argument you see, on Sunday morning shout shows where one person is saying one thing, one person is saying another, and they can't possibly agree. That we got to argue about the same number for it to be a sensible argument. And the question specifically says, has the number fallen? So has the new true population number fallen from 7.2? Yes or no? Okay, so that's the argument. And we're going to use, remember, statistics is using data to support arguments. We're going to use x bar as 7.05 with an n of 81. And we take sigma to be 0.9. And remember now, sigma is the population rating that we're taking to be the one person at a time standard deviation of the ratings. And we took 81 of those ratings and averaged them and got 7.05. Hypothesis test always works the same way. Always starts with the same 2 words. Assume H naught. So the person in the front of the room is saying to the people in the seats, assume you're right. I'm going to show you that my sample is so way off that it's really not possible to believe that 7.2 is the right answer. Okay? Now, from the assumption of 7.2, we get the sampling distribution. Then the sampling distribution is, and we always get a bell curve. It's always centered at what H naught thinks is the true number. And it's got a spreadedness that depends on the formulas. In section 6.1 we had one formula for proportions. In section 6.2 I just showed you a formula for when you know the standard deviation of the one person at a time numbers. You often don't know it, but sometimes you do. And the formula was sigma over square root of n. So in this case that's 0.9 over the square root of 81. So that's 0.9 over 9. So that's 0.1. Okay, I don't need a calculator for that. Okay, so all I got to do is figure out where is 7.05. Is 7.05 a way crazy low one here, or is 7.05 a perfectly possible just a sampling thing? So our sample is, try to draw the same picture, 7.05. And there's the p-value. Okay, so of course this is got to find the z-score, and then I'm going to use StatKey to look it up. So the z-score, z is x minus mu over sigma. And now here, what happens is I'm taking 7.05 minus 7.2. Remember, this is supposed to be the same picture. Over, now a person could be confused by the two sigmas. They are two different things. This is the standard deviation of the one review at a time numbers. This down here is the standard deviation of this curve. So in any event, down here I'm writing 0.01. That's the spreadedness of this curve, 0.01. So what do I get here? 7.05 minus 7.2 divided by 0.01, and bring out my calculator and see what it says. So 7.05 minus 7.05 minus 7.2 equals divided by 0.01. What? Divided by 0.1. Sorry. 7.05 minus 7.2 equals divided by 0.1 equals. There we go. And I got minus 1.5. So 7.05 is down there in the minus 1.5 range. And we know from our experience that minus 1.5 is a low z-score, but it's not a ridiculously low z-score. And so we know from doing lots of these problems that we expect to fail to reject. 7.05 is a perfectly everyday sample we will fail to reject, but I'm going to bring up StatKey and do the actual calculation. Of course I am. Oops. Hand on the wrong buttons. Let's see if there we go, StatKey. And this is a normal curve, so I'm clicking on normal. And what the heck was it? Minus 1.5. So I'm looking at a left tail because on my paper I just had a left tail, and I got to make that say minus 1.5. So minus 1.5. If I entered the numbers right, I get a p-value of 0.067. 0.067. So that's about between 6 and 7% for a p-value. Okay, let me get rid of that. Between 6 and 7% for a p-value. There we go. So p-value is 0.067. Fail to reject. Because 0.067 is not below 0.05. 0.05 is the kind of very typical number that you would use here if you weren't told to use any other number than 0.05 is the number you should use. Okay? So what happened here? So what happened here is that we are looking for answer questions about what is the true number today, 10 years on. Is it still 7.2 or has it fallen? We had some data. This particular data included the standard deviation of the one review at a time. And just like with the SAT, sometimes you know that number. Not always. A lot of times you don't. But sometimes you do. And if you do, here's how you do the problem. It's a very typical hypothesis test. You write down the sampling distribution. You figure out the spreadedness using the formula. It's on that page. Remember, there's one page that contains all the formulas. So you figure out the spreadedness using the formula. And then you find where your sample is. Is it a way out sample or is it a perfectly everyday sample? Ours proved to be a perfectly everyday sample. Getting there, but not far out enough, because the p-value is not below 0.05. Okay, so very typical hypothesis test kind of stuff. Very typical hypothesis test kind of stuff. So the kind of stuff that we're comfortable with now because we've done so much from chapter, oops, sorry, wrong one. So much in chapter 4 and, where's my, I got to uncouple this. That's what happened to it. Okay. So again, this happens sometimes. You see this sometimes, but it's not as common as the case where you don't know sigma. What's happening here is that I am in a context where I know the standard deviation of the one at a time numbers. And again, the SAT company gives this test, and they'll tell you that the standard deviation of one at a time numbers, they take everybody in the country took the SAT and they plug them all into the standard deviation calculation and they come out with 100. So sometimes you know sigma, sometimes you don't. More often, in fact, you don't. So we now want to move to the context where we don't know sigma in advance. We don't know mu, because we never know mu, that's what we're looking for, but we also don't know sigma. So in practice, we often don't know the standard deviation of the one at a time numbers. And I want to tell you a story about that gives you some idea of this kind of thing. So the Guinness Brewing Company. So maybe you don't think of it this way, but beer is an agricultural product. Every day, a farmer backs their truck up to the loading dock at the Guinness Company, and in the back of their truck, whatever is back there, barley, hops, whatever it is they make beer out of, I don't know. One farmer came from the lowlands, and today's farmer comes from the highlands, and it's all different. Not only does it have a different X bar, a different average amount of, let's say, fructose, but also today's farmer has a different variability in fructose. You go to the back of the truck, you go to the front of the truck, you go to the left side, you go to the right side with your test tubes, and you pull out 6 of them. Not only is it today's X bar of fructose different than yesterday's X bar of fructose, but also today's sample standard deviation. Today's farmer's variability of fructose is different than yesterday's. So you can't say just use such and such a number because that's always the variability on a per truck basis. That's not right. The variability differs from day to day. You'll get different amounts of fructose and different variabilities across the truck, and so you'll come out with something that's not a standard final product. The whole point of making the beer is today's beer is supposed to taste the same as yesterday's. It's supposed to have the same alcohol level because the fructose was processed by the bacteria, all this kind of stuff. Okay, so the Guinness Brewing Company in the beginning of the 1900s had the problem that they were not only looking to pin down mu, for, say, the amount of fructose in the back of those trucks, but they were doing so in a context where they didn't know sigma. They didn't know if you have these 6 test tubes and you walk away from today's farmer, they didn't know what is going to be the standard deviation of those 6 test tubes. They just didn't know it. I mean, that's just all there was to it. So they don't know the standard deviation of the population. They have to guess. So, of course, what you use for a guess is the standard deviation of the sample. The standard deviation of the sample, that's all you have, so that's what you have to use. Okay, the guy who worked for the Guinness Brewing Company, who was tasked with this problem, his name was Gossett, and he figured out what you have to do. That's today's twist. That's the twist for today's formulas. So he figured out what you have to do. You have to use some slightly different curve than we've been using other days, so-called a T curve. So he knew that this. He knew that this discovery was his chance at fame. And, that's why I know his name, because of this discovery. So he wanted to publish it. But the Guinness Brewing Company, this is just like today's kind of IP stuff, the Guinness Brewing Company didn't want to publish it because it gave them some advantage over other brewing companies. They got better beer. They got more sort of reliable amount of alcohol kind of stuff because they had this theoretical understanding that other companies didn't have. So they came to an agreement. They published, he was allowed to publish, but he published it anonymously. In those days, in the early 1900s, when you published in a scientific journal anonymously, you didn't sign it John Doe or anonymous or anything. You published it under the name A Student. So just a student. And as a result, and because he used the letter T instead of the letter Z, as a result, it became known as a student's T curve. Okay, so I'm going to show you. You simply have to go to a different place in StatKey and punch in the numbers. It's all the same ideas, confidence interval hypothesis, all the same ideas that they ever were, but you simply have to go to a different place in StatKey, that's all. Okay, so let's try it. So I want to do a confidence interval, and I want to do a hypothesis test, and here's the formulas. So the standard, the spreadedness is S over square root of n, the center is mu, just like it always is. And then the shape is, this says T curve, so I got to tell you what the T curve is, and I'll show you. It's on StatKey. It's just a question of bringing it up. And n minus 1 degrees of freedom. So n is the sample size, so we're always going to subtract 1 from n. And so, like I said, there's always a twist with these formulas. But this is no harder than any of the other things. exactly the same ideas. It's just a question of using it in a different place in stat key, that's all. So the big picture, what does a confidence interval mean? What does a hypothesis test mean? That's all the same. The little picture of where do I click, that's what I'm going through now, but it isn't hard. Nobody ever says to me I didn't understand where to click. Okay, so of course I want to do a couple of examples. Let me bring up stat key if I can manipulate my, there we go. Let me bring up stat key, that's where I was before, so I'm going to back out of that. And I want to, darn it, there we go. I want to show you the example that I'm going to use for confidence interval. So I'm in the book, and I'm looking at number 91. I need more light here. Let me put on the light. That's a little better. It's a dark day. Okay, I want to do here number 91. Just get rid of the stat key. There we go. Come on. There we go. And just so maybe a person can, I'll read it, but maybe a person can read it in their book. It says, domestic cats kill many more wild birds than scientists thought. Estimates the proportion of domestic cats that hunt outside. Separate study used kitty cams to record, a little camera they stick to the cat. Record 55 domestic cats. Video showed that the mean number of kills per week was 2.4. That's a lot of kills. The mean number of kills per week was 2.4 with a standard deviation of 1.51. Now that standard deviation is not sigma. So the point of what we're doing now is that that's a sample standard deviation. That's an S. 2.4 is an X bar. We've done an awful lot of those. I hope a person recognizes that 2.4 is an X bar. But this is the new part. This is not the population. This is not like the 100 for the SAT. This instead is the sample standard deviation. We did not test every cat in the world, so we don't know the variability of every cat in the world. Instead, we tested these 55 cats, so this is S. It says, give me a 99% confidence interval. Okay, so write all this stuff down. Go to the stat key and etc. Okay, so let's try it. What does it say? It says n equals 55, so I'm doing number 6.91. 6.91. So it's n equals 55. X bar is 2.4. And then the point of this section, the thing to notice is that this is not sigma, this is S. 1.51. So I know I said it a minute ago, but because it's the big point, I'm going to say it again, is that we did not test every cat in the world to find the variability in how many things they killed per week. This instead is a sample number from sample of size 55, not a sample number from sample of size 55,000. This is a sample number from size 55. So we think this number could be off. Well, of course, we've talked many times that this number could be off, but we also think this number could be off also. So we're trying to deal with two different things that could be off. And as a result, we can't quite use a normal curve. We have to use something that's close to, but a little different than a normal curve. It's called a student's t-curve. Let me bring it up. Of course, it's just a question of finding the place in stat key where it lives. Let me bring it up. Stat key, stat key, stat key, stat key, stat key. There we go. Okay. So a person looks at the stat key website and sees there a T. See the T? That's for the student's t-curve. Let me click on it. Sometimes I have a little trouble finding the darn thing. Whoops. There we go. Click on it, finding the darn thing. Okay, now first thing comes up and says select degrees of freedom. Do you remember that it said, on the slide, it said n minus 1 degrees of freedom. I have 55 cats. So I'm going to enter the number here, not 55, but I'm going to enter the number 54. And we talked about degrees of freedom before when we talked about standard deviation on the first day or two. It's perfectly sensible. There's a very good theoretical reason why you take one away. But for our purposes in here, it doesn't matter. You just simply take one away. If there's 55 cats, you write down 54 in that box. And that's always what you do. We're never going to do it different. Okay. Now, what do I want? A 99% confidence interval? So 99% confidence. It looks like a normal curve, but it's actually a little different. It says T distribution. It could say students T distribution with a degrees of freedom of 54 because there were 55 cats and I subtracted 1. I want a 99% confidence interval, so I want to find how wide do I have to be 99% of all cases. So that means I want this in the middle here to be not 95, but instead 99. Stack key has it come up to 95. I want it to be 99. Okay, so I'm clicking on, and I'm going to enter 0.99. 0.99. Don't enter 99. I've done that hundreds of times. Just enter 0.99. Okay? And what does it say now? It says 0.99, so that looks right. It says 2.670. So in previous confidence intervals, I had a number called Z star, and it might be 1.645, or it might be 1.960, or for a 99%, it was 2.576. Here, for this curve, because there are two things that we're unsure about. We're unsure about the true mean, and we're unsure about the true spreadedness. Because there are two things we're unsure about, you get a slightly bigger number there, 2.670. That's the number I need for my confidence interval calculation. All right? 2.670. So, you take X bar plus and minus, it's not called Z star, it's called T star. That'll be the 2.670 when I get a chance to write it down. And then S over square root of n. Now it's a question of putting the things in. 2.4 plus and minus 2. Oh, I forgot it already. Can you believe it? 2.670. 2.670 times S is 1.51 square root of 55. And now, of course, it's a calculator job. A person can fill up the calculator job, but it isn't. That isn't the hard part. The hard part is figuring out what parts you put where. So X bar, just like it ever was. This is the spreadedness of the sampling distribution. I gave you that formula. It's on the page in the book. That one page contains all the formulas. Bookmark it. So S over square root of n is the spreadedness of the sampling distribution. And where did I get the 2.670? And the answer was I went to that T spot. Why did I go to T? Because this is an S, not a sigma. So I went to the T spot, I entered 54, and then I clicked to figure out how to make the middle be 99. When I made the middle be 99, I got 2.670. Stack key told me 2.670, and that's it. Okay, I'm going to punch out the numbers, but come on, everybody in the room can punch out numbers. So I'm going to stop this at some point. So let's try 1.51 divided by square root of 55. So I'll take square root of 55 equals, put it on the bottom of a fraction, and multiply by 1.51 equals, and then multiply by 2.670. 2.670 equals. And of course, I could have punched the wrong button. Very easy to punch the wrong button, but I got 0.54. There's some more, but 0.54 will do for me. So I got 2.4 plus and minus 0.54. So up to something like 2.9, down to something like 1.9, and so we have a confidence interval. Let me try 2.4 plus 0.54. 2.4 plus 0.54 is 2.94. 2.94, and down to 2.4. 2.4 minus 0.54 is 1.86. And once again, well, there's a lot of rigmarole in the middle, and every one of these formulas has some small twist. But the twist here is that you have to look on a different curve, a different spot on stat key, and we need the 55 in order to do that. We had to change it to a 54. You always subtract 1. And we plug that in, and stat key told us that to have a middle of 99% required this number, 2.670, and then I punched a bunch of buttons, and who knows, maybe I did it wrong. But the big idea, always the big idea, is what's the point of that interval? And the answer is that we think there's a very good chance, not that X bar is in there, I know exactly what X bar is 2.4, but rather there's a very good chance that mu is in there. 99% chance If you went through this process 100 times, 99% of the time, the interval that you got would contain the true number. So I'm interested in the true number, not in the sample. I'm interested in the population parameter, not in the sample. Okay, so we think the population parameter is in that interval. So same thing, same idea as always. Some twists here for the different formulas. Mark that page in the book. Everything, you don't have to memorize it. Of course, none of that nonsense. Everything is open book and open notes. And the only point here, the thing that a person can be confused about is why. What is this? This is, we think that the population number is in here. We know what the sample is. We want to know what the population is. We think the population is in there. Okay, so always with confidence intervals, that's always how it works. We're interested in the population number. Okay, I also want to do hypothesis tests. Of course, I want to do hypothesis tests, and hypothesis test is going to call for the same kind of stuff. Here we go. Hypothesis test is going to call for the same kind of stuff. If I can find my there we go. Hypothesis test is going to call for the same kind of stuff. I need to do same thing with the S over square root of n. Same thing that we always do, only with S over square root of n. I got too many windows up here. There we go. So confidence interval we just did. Hypothesis test we're just about to do. So again, I happened to find a hypothesis test question in another book that I pinched from my office. So let's put it up. Okay, make it visible. There we go. Make it show up in the, there we go. There we go. And again, oh, it's not quite in focus. U.S. Bureau of Labor Statistics reports that the mean price for a gallon of milk, $3.34. Mean price for a gallon of milk, $3.34. Gallons of milk were bought in n equals 10 different cities, and then a test using level significance alpha equals 0.10, whether the population mean price for a gallon of milk is greater than $3.34. Okay, so the nominal number, the number we're arguing about is 3.34. We have a sample that comes up with a mean and a standard deviation that I'm going to show you in just a minute, and we're going to argue using that x bar and s. We're going to argue whether the 3.34 might be mistaken, and in fact the mean price for a gallon of milk might be greater than 3.34. Now this is a different book, so they use a somewhat different format. But so over here, it tells me what is the mean and the standard deviation and all that kind of stuff. So I'll copy that down onto the paper so that a person can see it. Okay, so we're arguing about 3.34, and we're arguing about means. So a person would know that we're in section 6.2 because we're arguing about means. So we have an H0 and an HA. And this is always the hard part. The rest of it, I know a person has to practice it, of course, but practice it and understand it are often two different things. The practicing part is typically not the part that gets people in trouble. It's the why did you do that kind of part. Okay, so this question asks about the average price of milk, so we're arguing not about X bars, but rather about mu's. If you tested every gallon of milk in the country, of course you can't test every gallon of milk in the country, but if you test every gallon of milk in the country, what would be the true average price? Always this is an equal sign, always, 100% of the time. And then what number are we arguing about here? I remember it as being $3.34. One group thinks it is $3.34. Another group thinks it's more than $3.34. Okay? These folks want to convince these folks that they're mistaken. Of course, statistics is using data to support arguments, so I have to write down the data. Let me pull it off here. It's X bar is 3.50. X bar is 3.50. The number of samples was 10, wasn't it? 10. And the sample standard deviation, that's not a sigma, that's not a nationwide variability, nationwide spreadedness, that's a sample spreadedness. And it is, it says here 0.4043. 0.4043. Okay? Okay. So I'm going to use the formulas I just showed you, but the formulas work the same way. Use the formulas I just showed you to run the hypothesis test. hypothesis always starts to say, I know I'm a bore on this subject, but it's nice to have a rock where you say, oh, it always does this. So assume H naught is right. Of course, the HA people want to show that's not going to turn out to be possible to believe, but we'll see. Okay. Then, to get from H naught is right to the sampling distribution is a question of mathematics. It's not a question of data. Then the sampling distribution looks like this. And if H naught is right, then it ought to be centered at $3.34. And the spreadedness ought to be S over square root of n. So that's 0.4043 over the square root of 10. What does my calculator say that is? .4043 divided by square root of 10 equals, I got 0.13, I'm going to call that 0.13, 0.1278, so about 0.13. Our sample, we need to find the p-value. So we write down where is our sample. So our sample, well, it's supposed to be the same picture. I really wish I was a better picture drawer. 3.5, $3.50, and that is the p-value. Okay. So I have to figure out how far out on the curve is it. So 3.50 minus 3.34 divided by the spreadedness of that curve, 0.13. Who knows? So 3.5 minus 3.34 equals, divided by 0.13 equals, and I got 1.23. Now that's not a Z, that's actually a T. Okay? So we have some experience now. Maybe a person might say, well, we're not familiar with the T-curve. But we have some experience that 1.23 is nowhere near 2. It's not out in the getting rare zone. It's still in the perfectly everyday, could just be a sampling thing zone. But anyway, I'm going to, of course, illustrate how you calculate what the p-value is by bringing up stat key and seeing how it goes. So let's see. Stat key. There we go. Come to Papa. There we go. Okay, stat key. And I want to back out just to remind a person how you find it. So I'm on the StatKey website, and I'm looking at where it says T. T? Okay, T. It says enter degrees of freedom, and this depends on the sample size. Do you remember that the sample was size 10? So I'm going to enter not 10, but it's 9. So there's perfectly sound theoretical reasons why you subtract 1, but for our purposes, you just subtract 1. And you get a curve that looks like a bell curve. It turns out it's actually a little bit sort of lower in the middle and higher at the sides, but it's pretty close. And we want to know, we want a right tail because the picture I just drew on the piece of paper had a right tail. And I don't know, I don't want 2.262. I instead want 1.23. Do you remember that I had a 1.23 for a score? Okay, so I'm entering 1.23. 1.23. And you enter it, and there's the p-value sitting right there, 0.125, about 12.5%. So that's not a Z, that's a T, but it plays basically the same role. Marks how far out I am on the curve, and it's not nearly enough to make a p-value that is below. Do you remember that the question asked me to worry about alpha equals 0.10 instead of alpha equals 0.05? Anyway, 0.125 is not below either of them. So let me bring up the piece of paper again, and we get a p-value of 0.125. Okay, so the p-value is 0.125, and that's not below alpha equals 0.10. This particular question, they asked me to work with that alpha. So you fail to reject. Fail to reject. Okay, so that proves to be a perfectly everyday sample in a context where the nationwide average was 3.34. If you took a sample of size 10, you could perfectly well get $3.50 for an average. It's perfectly possible there's a 12.5% chance of that happening. So do you convince these people to change their mind? They say, no, you're going to have to do better than that. Maybe take a bigger sample. Okay, very good. Okay, of course, I have the assignments on the on Canvas. Under the files, you go to Home Files, and it's called assignments_stats.pdf. So that'll tell you the three sections from the sections involving 6.2. One of them is called, for example, 6.2 HT. That's the hypothesis test section, and 6.2 CI. That's the confidence interval section, and 6.2D. That tells you the distribution. But so the point with those, notice when you do those questions. The point with those is that you are working not with the standard deviation of the underlying population. This is not like the SATs where you know sigma, where you know the spreadedness of the one person at a time numbers. That's not what these are. These are where you're working with S. This is more like the Guinness Brewing Company, where you don't know the spreadedness of the of the numbers that you're grabbing. So you have two things that you don't know, and as a result, you get a somewhat foggier picture, in which there's more possibility for error. And so you have to work with a slightly different curve. And I've showed you a couple examples of working with that curve. Okay, so taking a little break in terms of quizzes because of Easter, but we'll be back again next week. And I hope that everybody has a nice break, and I hope that everybody continues to stay well. Okay, bye-bye.